Yes, sir.
Yes, betul. Okay.
All right. I've got a couple of announcements. Okay. The first one is regarding the attendance. Okay. As you notice, if you check the Google Classroom, I have uploaded the attendance sheet, the collection of the attendance sheets from your submission for the last 3 classes. So please have a look. I've got a few students who messaged me regarding the attendance. Please do note that basically the attendance for the synchronization for this week, which is week 2, has just been updated this morning. So please check again your attendance. All right. So I just want to highlight attendance is quite crucial because this is on an online class. So basically, you can just switch on your phone and then you can go anywhere. So I have no idea what you are doing, whether you are listening or not for this session. So the best way to gauge or to check your understanding on the topic is either by the attendance submission or the impromptu quiz like the one that we just did. Okay. So please note that it's very, very important that you submit the attendance. For the first 2 weeks, I understand that some students might have some difficulties transitioning from home. Basically, you are coming back from home to campus, or maybe you are still I'm not sure about the classes, whether you want to join or you can join or not. So I'm quite lenient for the first 2 weeks because I understand you have several limitations. Okay, but starting from next week, we'll be more strict on the submission. Sorry, not submission. We'll be stricter on the attendance. So basically, we'll follow the university rules. You can see at the end of the attendance sheets, there is a column basically that denotes if you did not attend for how many sessions. Then you'll get first warning, second warning, and then you'll be barred from the final exam. So we're going to follow that. All right. So please make sure you check your attendance. I'll try to update the attendance by late Friday evening once I take into account the attendance for the Friday session. Okay. So please always check your attendance. The data for the attendance basically I collect or I extract based on the form that you submitted, the quiz. So it's not quiz, attendance form. So if you did not submit or if you submit, if you fill out but you did not press the or click the submit button, then I cannot do anything about it because I just copy and pasted the data that was extracted from the form. Okay, so that's about the attendance. So please pay attention to that. So number 2 is regarding the registration for this course. Okay, I think Dr. Rizwan, PR, has mentioned this a lot of time as well as providing message in the WhatsApp. Basically, for those with UR or for first-time student taking Thermodynamics 2, you have to register for MMJ240. Is it 2? Sorry, yeah. Put again 22. Sorry, yeah, 224. MMJ22403. So this is for first-time taking. Okay, if you are taking this course for the first time, so please register by using MMJ. But for those who are repeating, please use or please register by using the old code, which is EN243. So from the system, I can see that there are about 3 or 4 students who are still registered under MMJ, even though they are repeating. Okay, how do I know they are repeating? Because their code is RK08. Okay, because RK08 is the old code, so you should be registering using the old one. Okay, if you are repeating. If you are not sure, please contact your RPS. Okay. Okay. For new students, I think it should be clear. But if you are not sure, if you are repeating or if you are still under RK08 code, please contact your RPS for confirmation. Okay. Please do so as soon as possible. I just realized my first week attendance was failed. I just read submit now. Okay, a message from student. Again, that's what I just said, Wong. it is your responsibility to double check to make sure that you submitted your attendance properly. Okay, if you are not sure, just make sure you submit twice or 2 times. Okay, I know it's quite a hassle, but that's the only method that I can know that students attended, watch the video, and then answer the attendance questions. Okay, so please, starting from next week, there should be no more excuses like the submission failed, so I just will submit. Okay, because late attendance will not be entertained. All right. Okay. So the next one is regarding the test. If you notice, I've put a message or post in our Google Classroom class, Google Classroom platform. Excuse me. So our test one has been rescheduled, has been moved to a earlier date, which is on the 30th of November 2021. This should be on Tuesday at 19:30 until 21. So 7:30 until 9 o'clock in the evening. Okay, the location will be at DK. So please make sure you put this in your calendar and understand that, of course, this is part of your assessment. So I think this one is 10%. Okay, so please make sure you put this in your calendar and notify your lecturers, other lecturers, if they are planning to use this session. Because previously, when we put in the first date that we set, which was on, I think, on Wednesday, or is it Thursday, it clashed with another class. Okay, so hopefully you can basically be prepared. You already know the date of the test and be prepared towards the first test. Okay. There's one thing. Oh yeah. Okay. So if you remember, according to the schedule, we will have the industrial lecture, okay, given by people from the industry. So the person has been basically confirmed. So just again, remember, I think this is week 7. This is also will be on week 7 during class on Friday. Okay, I understand that most of you might be buying tickets for midterm break and so on and so forth. But please remember that this will be conducted during the lectures hour, which is Friday 10 o'clock. So it is compulsory. The lectures will still be going on Friday. So the attendance is compulsory, and there will be quiz based on the lectures given. Okay. So got question. Okay, so from Yusmi, a question regarding tutorial. Okay, from the briefing, tutorial will start at week 3. Next week, academic tutorial. Okay. All right, thank you, Yusmi. Okay, so regarding tutorial, I just had a discussion with the lab yesterday. All right, so for tutorial, will be conducted in week 4, Yusmi, not week 3. Okay, so that we have ample time, because we haven't finished the first 2 chapters yet. So I'm hoping that we can finish Diesel as well as Brighton before we start tutorial. Okay, otherwise, if we conduct tutorial next week, the content that's going to be covered is not much. Okay. All right. Okay, I'm having problem with my internet. Okay. So tutorial will be in week 4. Okay, use me. And our lab, okay, will be in week 5. This is our first lab. The details of the lab will be provided soon, but basically we will be having 5 lab sessions, and please join the session according to the group. Okay, the session has detail out basically X diploma, group 1, group 2, and then all the specific groups. And then there are a few students. Okay, okay, that's one problem. I have trouble with my internet. Okay, there are a few students who have contacted me, informing me regarding the basically request to change a lab session or tutorial session. I'm okay with it, to be honest. As long as you can accommodate lab according to your schedule, it doesn't matter. Okay, but please, if possible, stay to the correct group, because the group has been given to ensure that we don't have too much students in one particular group. Okay, we have 125 students. If all students basically just join group 1 or group 2, then we'll have about 30 or 40 students per group, which is not possible to adhere or to follow the SOP. Okay, so unless you have contacted me, email me requesting or informing me about your clash and you have to join other session, those students, please go ahead as your plan, but the rest, please follow the set of group that you have been assigned to. Okay. All right. Any other questions from students? So I can see that we have quite a few questions. Any other questions? You can just type your question in the chat box if you have. Anyone else? Ada? Okay. All right. So if that's it, okay. Let's go have a quick recap on the asynchronous session, what was covered and the importance of it, so that we can understand when we move into this one. All right, so basically we stopped up until here during our last class. Okay, so basically we look at the reason why we are focusing on the idealized cycle, because it simplify our analysis. Okay, so instead of looking at the real cycle, how the real cycle behave, we are more interested, or we make several assumptions that can be used to look at the idealized cycle. Okay, remember, idealized cycle is not feasible, or it's not possible to be replicated in the real scenario, in the real world, but we use it for the sake of simplifications and also to check what is the maximum output possible. So it's similar to like Carnot. Okay, it's not possible, it's reversible. Reversible means after if, for example, we move the piston until one location, then the piston can move back to its original position. In reality, we have a lot of losses. The process itself is called irreversible. Okay, so idealized cycle is a reversible cycle, means that it can goes back to its original position. Okay, even though in reality that's not possible to be achieved. Okay. So I'm not going to go into details because you should have watched the video that I have posted and I've instructed you during this async section. So I'm just going to cover the important parts for recap. Okay. So we look at the assumptions that we make. So this is one very, very critical assumptions that we use for the analysis in the gas cycle. Okay. So the air standard assumptions, it basically tells us the simplification or assumptions made in order for us to proceed with Otto, diesel, as well as Brighton cycle. Okay, so otherwise, for example, if you are dealing with the real cycle, okay, air fuel mixture itself is not air alone. Okay, for idealized cycle, we are considering the fluid is just air. But if we consider the real mixture, it should be a mixture of several gases. Okay, plus it's not just air; it's air plus fuel in reality. Okay, so that's one simple simplification that we make, and then we assume it to be reversible. So when we talk about Otto, diesel, Brighton, and later on Rankine, these are all idealized cycle. It means that it's not possible to be achieved, but we do it for the sake of analysis. Okay, in real life, these cycles, the real cycle is irreversible. It means that once some losses, once friction happens, it's almost impossible to undo the friction, right? Once friction or wear and tear happens, we have no way to basically make the parts new again. So that's irreversible. Okay, so that's due to the friction, heat loss, so on and so forth. Then in real life, Akid, could you please mute your microphone? Okay. Okay. Then for the system itself that we are looking at, it is assumed, or it's in terms of a closed loop. Okay, because if you look at the last time when we look at the system, how the four strokes analogy works, we have intake over here, and then we have exhaust over there. So by definition, or by looking at the system itself, we know it is not a closed loop. It's an open loop because we have intake, we have outlet for the exhaust. Okay, but for the analysis, we assume it to be closed loop. Okay, this is in real applications. Okay, the important parameters, one of the important parameters that you need to understand for Otto cycle is this one, R. Okay, so R is compression ratio. Okay, so in the test, in the quiz, so usually they will mention compression ratio given is blah blah blah. Okay, but if the term is not given, just by, for example, the engine is operated on the for example, the R for the engine is given as 8, for example. Then you should know what is R, what R refers to. Okay, so R is a compression ratio, is one of the most important parameters for our analysis, okay, for this course. And the R is defined by the Vmax divided by Vmin, the maximum volume divided by minimum volume. So if you remember our terminology that we learned about the chamber, the piston, Vmax is when the piston is at the top, BDC, sorry, bottom dead center, at the bottom. Okay, so bottom dead center, that's when we have the highest volume. Okay, so the smallest volume is when the piston moves up and reaches the position top dead center. So the ratio between this bottom dead center and top dead center, that's what we call as compression ratio. Okay, so in the analysis, when we look at the TS or PB graph later on, you can basically just use R equals to V1 divided by V2. Okay, so because if you remember the plot, we have something like this. So this is 1, 2, 3, 4. So this is V, this is P. So you can see that the volume at 1 is larger than the volume at 2. So R equals to V1 divided by V2. Okay, so always remember that. Then we talk about the compression ratio, which is basically what I asked just now in the quiz. So compression ratio, again, basically is an indicator of the power that it can be produced by the engine. So typically, for Otto cycle, so you can see over here, this is the limit or the range allowed for the Otto cycle. Okay, between 8 to 11 roughly. Okay, so between 8 until 11. And if you look over here, if you plot here, this is again, if you look over here, that's the efficiency for Otto. And remember, Otto is idealized cycle. It shows up until between, let's say this is 8, roughly about 55 to 60% efficiency, which is impossible in real life. Okay, so please remember that. In real life, basically, the efficiency for gasoline engine is about 20-25%. So it means that, for example, for every ringgit, for every dollar that you fill up your tank, you only get back about 25% or 30%. So 35 ringgit, 35 cents or 25 cents out of 1 ringgit that you spend for your gas. So the rest basically is lost in terms of frictions, in terms of irreversibility, in terms of heat. Okay? So just to show that even with now is 2021, even with this technological advancement, we are still basically cannot get a higher output for our engine. Okay? Later on, we're going to look at a diesel engine, which basically typically can produce a higher efficiency, a bit higher than Otto. Okay, but if you could look over here, the question is why can't we use a higher compression ratio? Okay, so I think we discussed this in the video. if we use a higher compression ratio, it has problem in terms of what we call as knocking. Okay, so knocking is basically the auto ignition. So instead of ignition or combustion by the spark, now fuel or the air fuel mixture combusted before the spark plug basically works. Okay, so that's what we want to avoid, because auto ignition or the knocking basically cause uneven combustion. So just imagine if you have a chamber like this, okay, and let's say this is the position of your piston. Okay, this is your piston. If you have uneven combustion, okay, the star that I drew over there, so the spark, or sorry, it's not the spark, the ignition can happen at uneven or at a random location. So after a while, because the combustion that is happening, or the ignition that is happening not at even surface or at even location, so after a while, the wear and tear of the engine or the piston, or in this case the cylinder, will be expedited. Okay, will speed up. So maybe instead of 10 years, your engine needs to be overhauled or replaced after 2-3 years. Okay, so that's the problem with auto ignition, okay, or knocking. Additionally, if you use a higher compression ratio, means the P is higher, the pressure is higher. So a higher P basically requires a bigger engine block or a more robust material. Okay? And that's what makes the difference between the gasoline engine and the diesel engine, which is based on the compression base. So we are going to look at diesel engine in a moment. Okay? So if we increase the compression ratio for Otto cycle, so we have two main problems, which is the knocking, as well as the engine itself, the materials that needs to withstand the high pressure needs to be changed basically. So instead of having a certain size, we may need a bigger or a thicker material or dimensions for the materials for the Otto engine. Okay. All right. So next is MEP. MEP is again one of the critical parameters that will be used a lot. What MEP is basically just the mean effective pressure. So again, do not be misled or misunderstood about the term mean effective pressure. It's not about pressure at all. So the term is basically given by this equation. MEP basically equals to W net divided by displacement. So we know we can find W net. Displacement is just Vmax minus Vmin. Okay? So we are going to have a look at one example problems where we need to calculate MEP, and usually you need to calculate the volume over here by using the ideal gas equation. We are going to have a look later on. Okay? So this W net, if you remember, if you look at our graph over here, W net for constant pressure is given as W equals to P delta V. If you remember, for the constant pressure work, okay, work under the area. Okay, so if you have shaded area here, so this is the work, and we can calculate the work by using W equals to P delta V. So if you translate this, P and delta V, substitute delta V is basically just piston area multiplied by stroke, displacement up and down, and you get the following equations. Okay, so we're going to look at how this is used. Okay, so this is the equation that we can use to calculate the efficiency of Otto cycle. Okay, I would like to emphasize this is one of the examples, not the equation. Okay, because we have two ways to calculate the efficiency. One is by using this equation, and this, if you remember, R is the compression ratio, and K from term 1 is basically the ratio between Cp and Cv. And if you remember, Cp and Cv is basically an approximation for the air properties at room temperature. So K usually is 1.4 for air. Okay, if you look over here, 1.4. So this equation basically is a shortcut. If you want to calculate the efficiency, we can use this equation by using some approximation. So the value is not that accurate, but it's a shortcut. Okay, we have another method basically to calculate the work. If you remember, the work basically is just W net in divided by WQ out. W out work equals to W out divided by Q in. So this basically is another way that we can use to calculate the work, okay, which can be translated into the efficiency. So there's one example problems that we're going to do that we are going to analyze basically based on these two perspectives. Okay, so basically I think that's where the video stops. So basically, for today's lesson, we're going to focus on the diesel engine, and then we have a look at one example problems at how these parameters, the one that we just looked or studied, can be used to analyze the auto and diesel cycles. All right. So just to recap, one of the main difference between the properties or the working conditions of the auto cycle and diesel. Okay, so basically gasoline uses the auto cycles. Diesel basically is a diesel cycle. Okay, so for gasoline, we have spark plug. Okay, so what happens is when the compression happens, okay, once the piston reaches the top dead center, the highest position of the piston, then spark will combust the mixture. Hence, you have the power, okay, the push back down and then the exhaust. On the other hand, for diesel cycle, when compression happens, the only thing that the piston compressing is just the air. Okay? So the main difference is in terms of the mixture. So when the piston reaches top dead center, only then the fuel is being injected into the chamber. And once the fuel is injected into the chamber, because the pressure at that point is very, very high, then it will automatically combust. So there are a few differences that we can highlight. First, between auto versus diesel. One, of course, in terms of the fluid. The fluid being compressed. Okay. For auto, it is air fuel mixture. And for diesel, it's just air. What else? Okay. The difference, other than the difference, is in terms of the compression or the pressure. Okay. Because for diesel, the compression, okay, basically the compression, the pressure due to the compression is very, very high. So when the fuel is injected, it will automatically combust, okay, compared to the auto cycle. Okay, so pressure very high for diesel. So for auto, P auto is less than P diesel. Okay, and then of course, spark plug and spark plug is only for auto or gasoline. Okay, so these are the main differences. So other differences, of course, you can relate to this point. For example, once we have a high pressure, okay, so you basically cannot use the same engine block or the same material for the auto and diesel. So for auto, or sorry, for diesel, because it has to withstand a higher pressure, so the material is more robust or thick. Okay, right? So that's the other basically relationship between high pressure and the materials. Okay, so because the pressure is very, very high, so it needs a material that can withstand the high pressure. Okay, all right. So I think we have a video over here. So let's have a quick look. Okay, so you can have a look over here on the video. Basically, instead of having spark plug in the middle of the chamber, now we have fuel being injected. Okay, so just look at over there during the intake, what is being sucked into the chamber is just air instead of air fuel mixture. Okay, so this will be reflected in the PV diagram that we are going to look in a bit. Okay, all right. Okay, so if you look over here, this is the PV diagram for the diesel cycle. So what you notice over here is that instead of having a control volume, okay, so let me draw it quickly. One, two, three, four. This is for auto. So the main difference is this part here. Okay. Over here, we also have Q in, Q out. Okay. So over here, instead of having control volume, now we have a constant, it's not control volume, sorry, constant volume. Now we have a constant pressure. Okay. So why do we have something like this from 2 to 3? So if you remember, from 1 to 2, it is, okay, from here we can see that it is isentropic process, isentropic compression. So just a recap, isentropic basically means it is adiabatic and reversible. Okay, so this is back in thermo 1. Okay, so from 1 to 2, you will have isentropic compression. Okay? So the piston basically is compressing just the air. Just remember that. Okay, this is for diesel. So 1 to 2, isentropic compression of the air. Okay, now, once it reaches or almost reaching the top dead center, now the fuel is being injected. So basically, at here, so this is from 2 to 3, I enlarge it a bit. So what happened is, this is just air. Okay? But once it reaches the top dead center, what happened is air plus fuel. Okay, so that's basically is being represented by the Q in. Combustion happens. So that's why you have an enlargement or an addition of volume. So if you see here, the volume at 2, basically it expands. So from 2, it moves to 3. So there's an increase in volume. So V3 is larger than V2. And this is because instead of just air, at point 2, fuel is now being injected into the system. So that's why fuel plus air, the volume now expands. Okay, you have an extra volume. So that is represented by this process, a constant pressure heat addition process. Heat addition because, of course, when fuel is being injected, now combustion happens. Okay, so it expands until 2 to 3. Next, after that, 3 to 4. After the combustion, of course, the gas expands, it pushes down the piston to go down. So it becomes isentropic expansion. Okay? And 4 to 1, finally, is the exhaust lah, basically, is the removal of the heat from the system, which is Q out. Okay? All right, any questions from students based on what we have covered until this slide? Any questions? You just type in the textbook. One. Okay, all right, so let's proceed. Okay, so aside from PV, of course, we can also use a TS diagram, but commonly, usually for auto or diesel cycle, usually is more common to use the PV diagram. Okay, TS diagram, usually we use it for Brighton and also for the Rankine cycle. Okay, but either way, it's quite similar. Okay, so if you see over here, this is in terms of S entropy. Okay, 1 to 2, it is constant entropy. So you have 1 to 2 is isentropic compression. When you compress something, it increases the temperature. So from 1 to 2, temperature increases. And 2 to 3, similarly, you have the fuel being injected. So again, it expanded. Okay, over here, P is constant. So 2 to 3, heat is being injected over here. And then next, 3 to 4 is expansion. When expansion happens, basically, it loses energy because the basically the gas expands. Okay, doing work on the system, it pushes down the piston, so it loses energy. So from higher temperature to a lower temperature, and finally exhaust or Q out. So you have 4 to 1. Okay, as a constant volume. All right. Okay, now this is very, very important. Okay. What we have learned so far in auto and also diesel, in order for us to properly analyze them, we need to understand some of the materials, some of the equations that was already covered in Term 1. So now I'm just going to quickly highlight some of the equations in entropy, basically chapter 7, Term 1, that you should understand that will be used for analysis in Term 2. Okay? So, for example, of course, this is the basic first law. We know the ideal gas relationship, PV, MRT. And then this relationship is quite important. The entropy relationship, which I'm going to show in a bit, the details. Change in internal energy, change in enthalpy. Enthalpy is H. Okay, when we have a constant pressure, we can use basically this following equation: constant specific heat or constant volume heat, Cp or Cv. So we can use Cv du dt or Cp du dt in order for us to simplify our equations. Okay, so we look over here. Okay, I make some short analysis. Okay, what can be used from our knowledge in Term 1 as well as in Term 2 and apply to our analysis. Okay, for example, this is for auto cycle. This is for auto. I want to highlight this. Okay, for example, for auto, 1 to 2 is isentropic equations. So if you remember back in Term 1, there's one equations that we can use for isentropic equation, which is A. Basically, A here refers to the first method, and B here refers to the second method. Okay, so this is the first method. Okay, this is isentropic equation. Okay, Tu divided by T1 equals to V1 V2 K minus 1. Or we can use the second method, which is by using the relative volume. Okay, so V2 divided by V1 equals to VR2 divided by VR1. Okay, so I'll show you in details what is A and B about, but this is basically a recap from Term 1. Okay, and next we move to 2 to 3 for constant volume heat addition process. Okay, if you remember, you look carefully over here. This is a constant volume process. So constant volume process, if you do the equations, you're going to get Q equals to delta U. Okay, we have not work being done because if you look at the here, okay, there is no area under the plot, area under the graph. So the work done by the system during constant volume process is 0. So you only have Q equals to delta U, and you can simplify because if you look over here, delta U dt equals to the Cv. So you can use Cv T3 minus T2. You can use this equation. Similarly, for 3 to 4, we have isentropic. Okay, so when it says here isentropic, So that's the keyword. So you can use isentropic equation. So the A here, T4, T3 equals to V3, V4, K minus 1. Okay, that's the first one. Or you can use the relative volume, okay, method B. Okay, finally, for 4 to 1, constant volume heat removal. Again, similar to 2 to 3, because it is constant volume, you have no work. Okay, when you have no work, you can use here, okay, CV du dt. So you can use CV T1 minus C4. Okay. So the question is, what is the difference between method A and method B? Okay, method A, here, if you look at the equations, when you see something like this, K, if you remember, K equals to Cp and Cv divided by Cv. And for air, the value of K equals to 1.4. And this is basically approximated at room temperature. Okay. So the keywords here is approximated. Means that for this, basically, this is approximation. Okay. It speed up the process of calculation, of course, because you can just plug in the values. You should be getting the answers or the variables that we need. But it is an approximation. On the other hand, if you look at method B, if you look at here, VR2 and VR1, this is basically exact analysis, because the variables, they are dependent on the temperature at the specific properties. So for example, excuse me, if you want to find VR2 or VR1, we need to know the exact temperature of VR1 and or VR2. Okay, so there's one example problems that we're going to have a look that basically show you, okay, how to use these particular equations. Okay, all right. So that's the main difference. One is the approximation, okay, because we have K here, and the other one is the exact analysis because you need to find the temperature. Okay. All right. So let's take 5 minutes break, and then we are going to continue with our lecture. All right. So 5 minutes, everyone. Thank you.
Here then.
Okay. Before we continue, I've got a few emails from students, especially those who have just registered or joined our course for the new intake. Okay, so all right, so the Ridwan already mentioned about this. I totally forgot. So for those who have just joined this session or just joined our program, I was made to understand they joined on the 25th, so just about 4-5 days ago. All right. So for those students, okay, you have the first thing that you need to do is to watch the videos or the recording videos of our previous sessions, which are all available under the Google Classroom. Okay, so please do that. Okay, so now since this is already week 2, so those students have 2 weeks to submit the quiz that we just done just now. So don't worry about being late. So you have to watch the videos and please submit the quiz once you have watched up until the 3rd video, which is first is briefing, then the last week on Friday, and then on Monday this week. So 3 videos. Okay, so you have 2 weeks to submit the quiz. All right. Any questions from new students? Anyone? Okay.
No, Doctor.
All right. Thank you. Okay. So let's continue. Okay. So just now we just look at the 2 methods that can be used for analysis. Okay. Whether it is approximate or the exact analysis. So when we do the example problems, you're going to see that basically by using this approximation method, this one, basically it speed up the process and you can do a much quicker calculation. Okay, of course the value might be different because we are doing approximation, but they are still reasonable and within the range or acceptable range. Okay, however, it all depends on the question. Read the questions carefully to understand what is being expected. Okay, the problem with students last time, when the test clearly ask you, for example, to use or to account for the temperature variation, for example. When you account for temperature variation, that's the keyword, you should look at, or you should understand the keywords. Okay? Account for temperature variation. Okay? Just by looking at this, you know when using K, you are not going to account for the change in temperature because it is approximation. So when you want to account for variation, means detailed analysis, you need to use this method B. All right. Here are some tips. Students, sometimes you are confused because there are quite a few equations that you can use, and then we have a lot of cycles that you have to analyze. Sometimes you don't know which equations to be used at what particular cycles or what particular stroke, for example, you want to use. Okay, so there will be 3 tips that I'm going to share. The first one is regarding the ideal case equation. Okay, remember, because we are doing these cold air standard assumptions, basically we are assuming that we are dealing with air. So air is behaving as ideal gas. So basically, you can use ideal case equation, PV equals to MRT, for all the strokes or for all the process 1, 2, 3, and 4. Okay, so ideal gas basically you can use on all the processes. Okay, because remember, in these cycles, we are assuming the fluid to be air. Okay, so that's first one. The second one, the isentropic equation that we just discussed. So there are 2 analysis or 2 methods that you can use, approximate or the exact analysis. This basically depends on the question. If the questions basically specify in detail, okay, mention clearly, for example, the keywords, account for the temperature variation. Okay? Because the temperature basically varies and you have to take into account of that variation, then you know this is what you need to do. Okay? But if the questions did not say or just ask you, okay, calculate the efficiency for Otto cycle, for example, very, very general instruction, then you have a choice. You can use approximate analysis or exact analysis. Okay. Sometimes it might mention, okay, assume or use the constant specific heat approach, for example. Then you know you can use the approximation method. Okay. If the question basically did not give any indication to take into account the variation or specific heat, then I would suggest you to go for this method because it is much, much quicker. Okay. One example that we're going to look in a bit basically requires us to decide, okay, you need to look at the questions and understand what is being expected of you, and then you will see the equations that we're going to use, okay, and how different it will make in terms of the calculations. Okay, and finally, about the constant specific heat. Okay, when can you use this CV delta T or CP delta T? So if you notice, the hints is on the variables here. CV, you can use it whenever you are dealing with constant volume. Okay, for example, this is for auto. You have Q in, you have Q out. Okay, but for this is auto. For diesel, you notice that this is Q out. Your constant volume is only at over here. This is constant volume. So over here, you need to use constant pressure equation, which is Cp delta T. This is Cv delta T. Over here, Cv delta T. Over here, Cv delta T. So that's it. So you need to know where to use it. So sometimes students are confused, you don't know, and then you just blasah, you just use whenever that you want. So it makes up the whole equation. Okay, so these 3 tips, I think hopefully it helps you to make your decision. Ideal gas equation, you can use pretty much use it for all processes, 1, 2, 3, 4, because we're dealing with ideal gas. Isentropic, the keyword is here, isentropic. You can only use this on isentropic processes. Okay. In our case, isentropic processes refers to this region. This is isentropic, the red one, the one that I'm highlighting, and these are isentropic. So only on this red region can you use the isentropic. So this one is isentropic. Okay, other than that, for example, this is 2, 3, this is 3, 4, 4, 1, you cannot use this for isentropic. Okay? You cannot use this for isentropic, right? Because they are not isentropic. This is only isentropic. Okay. And then finally, constant specific heat. Only when we're dealing with constant volume, you use Cv. Constant pressure, you use Tp. Okay. All right. So again, this this is basically a screenshot or summary of entropy or isentropic processes. I think this is chapter 7 back in Thermo 1. So just for you to recap, okay, to understand. Okay, if you remember, this is what we're going to use for isentropic processes. If you look over here, it's already highlighted ideal gas and more importantly, isentropic processes here. Only for isentropic processes. Please remember this. Okay, do not use this for other processes. Okay. Okay. I have to highlight this. Isentropic is only for isentropic processes. Okay. All right. So this will be used in our equations. Okay. Student might ask, okay, do you need to memorize this? Okay, don't memorize, but make sure you understand it. Some of the equations will be provided in the midterm exam, so you don't have to worry about it. Okay, I don't expect you to understand or to memorize this, but I expect you to understand where or when to apply these equations. Okay, all right. So these are isentropic processes. Okay, okay. So isentropic processes, when you are dealing with K, as I said, it's all about approximation. So, but how about when we are dealing with a temperature variation, when you want to account the change in temperature into your calculations? So then you need to use the relative pressure or relative volume. Okay? So if I'm going to share quickly with you, if you still remember this. Okay, this is table A17 from property tables. Okay, if you look over here, so when you're dealing with ideal gas, you have T, temperature, enthalpy, PR, that's relative pressure, you have U, internal energy, and you have VR here. So this is what you just saw just now, VR2, for example, VR1 equals to V2, V1. Okay, so you can assume your volume 2 is approximately the same as VR2, relative volume. Okay, so that's what VR is. Okay. All right. So when we want to use exact calculation, then we have to use table A17 by using the relative pressure or relative volume. Okay. So this is the isentropic processes again. What makes this difference from this one is that this is an approximate analysis. Okay, because we're dealing with K. K is an approximation. The other one here, this is an exact analysis. Very detailed and long calculation. Okay, so it depends on the question. Okay, so all right, so similar to the Otto cycle, that's why if you remember previously I said for the efficiency, it's one of the method to calculate the efficiency for Otto cycle by using the given equation shortcut. Similarly, for diesel cycle, these are the equations that you can use to calculate the efficiency. Okay, where in this equation, R is the compression ratio, that's V1, V2. RC is the cut-off ratio. So if you remember, for diesel, 1, 2, 3, 4. So RC is basically V3 divided by V2. This is RC, cut-off ratio. So the volume after the fuel is injected divided by the volume of the air. Okay. So V3 basically, if you look, is air plus fuel, and V2 is just air. Okay. And K is again Cp over Cv, which is usually 1.4. Okay, all right. So some notes over here. Okay, the efficiency of the diesel, as I said, usually is much higher. But even with current technology, the highest that we can go is roughly about what, 35-40%, and Otto is about 30%. Okay, I think in the asynchronous video I mentioned about the Sky Active technology. Okay, currently apparently they claim to be the highest gasoline engine that provide the best efficiency. I think they can reach up until 30 or maybe 35% efficiency compared to other engine. Okay, so this is from Mazda, by the way, Mazda. Okay. All right. Okay, so now if you look here on the slide, sometimes we wonder, how do they come up with the shortcut, for example, the equations that we have over here? How do they come up with it? Okay, how do they arrive at 1 minus 1 divided by RK minus 1, all this? Okay, similar to Otto. Okay, all that basically starts with the energy analysis, the one that is quite familiar that we did in 201. So for example, we start with the simple equation here. This is for diesel. For example, if we are considering just at this position or cycles, process 2 to 3. So we have Q in minus W B out. If you remember, W B out, this is a constant pressure process. So we have work done. Okay, so we have a value for work. So work equals to P delta V. Okay, so from the equation, Q in minus WB out equals to Q3 minus U2. And if we simplify, we arrange everything to get Q in. So remember, your WB out is P delta V. Okay, this is what we have over here. And then you have U3 minus U2. And if you remember the definition of enthalpy, H equals to U plus PV. So you arrange everything, you're going to get H3 minus H2, which again, if you remember, this is constant P. So you can use the CP term, constant specific heat at constant pressure. So Cp T3 minus T2. So that's how you arrive at this equation, which is very critical for you to understand. Okay, next, if we analyze for the Q out, so negative Q out, negative because the heat is being rejected, exhaust, equals to U1 minus U4. Okay, to get Q out, so basically you bring the minus sign into the equation, you get U4 minus U1. And if you look over here, when we are dealing with U, so we get CV T4 minus T1. Okay. And the efficiency is basically W net divided by Q in, the output divided by input. So output divided by input, that's the simplest term. So when you expand it out, you'll get something like this. From 1 minus Q out, Q in, you expand, you know Q out is T4 minus T1. Substitute everything, you'll get something like this. Okay? And because we understand from RC equals to volume 3 divided by volume 2, substitute everything, that's how you arrive at the final efficiency equation. Okay? So it all started from like thermo 1. Q in minus W out, delta U, delta H. So all that came back from the basic thermo 1. Okay, so a bit of discussion on the advantages or disadvantages of diesel cycle. Okay, well, we understand by now that for diesel, the efficiency is a bit higher, yes. And of course, if you notice as well on the road, most of the trucks, trailers, all those big vehicles, they use a diesel cycle because of the performance. No high-tech electrical ignition system, increased longevity and durability because the engine itself is very, very robust, very, very thick. And then what else? Generate relatively low CO2 and CO emission. This is again depends on the type of diesel fuel that you use. I think right now they are using, is it Euro 6 right now? Euro 6 fuel, if I'm not mistaken. Okay. But disadvantages of diesel, again, in terms of design, it must be rugged or robust to withstand higher compression. Okay. And heavier because you make a lot of materials. And of course, because it's big, heavy, it is a bit costly. More noisy. Okay. This is apparent from the trucks. Previously, I think 20 years ago, diesel is much, much cheaper than gasoline. But right now, that's not the case. And then the disadvantages, of course, it produces or it the exhaust basically contains all these toxic chemicals or toxic particulates, such as the one over here. We have carcinogens and NOx. Okay, so for example, just show quick animations. Okay, so I think 20 years ago, I think this is quite common. The trucks at that time, they emit this huge soot. The black smoke is what we call as soot that contains particulate. So this particulate basically is like in Malay we call it serbuk lah, particulate tu. So it can be very, very harmful, especially for example if you are a motorist, you ride motorcycles, and you basically just inhale this particulate. It will be very, very harmful on your lungs. So that's why right now in terms of the advancements of technology, they have come up with Euro 6 or Euro 5 fuel. So what this signifies basically is the amount of particulate per million. So how many, so for example, they have a unit, how many particulates can, the maximum particulates can contain within that particular dimension. Okay, previously for Euro 1 or Euro 2, 20 years ago. So basically, I think we can have a quick guess that the particulate probably would be filling up this one dimension. But nowadays, because of this filter, it's not filtering, what is it? Penyulingan, based on the technology that they have, so the refining, the refinement of the fuel, diesel, is getting better and better. Hence, we don't see much of this particulate or soot anymore on the road. Okay? But of course, trucks in Malaysia, it can be 50 years old. So it doesn't matter if they use Euro 6, but the technology or the engine is still old. So it doesn't matter the type of fuel. Okay. All right. So I'll try to be quick. All right. So nowadays, in order to improve the diesel engine, Instead of having just constant pressure, now they have a mix of constant volume plus constant pressure process in order to improve a bit of the efficiency. I think most of the modern diesel engine, they are implementing this type of cycles. Okay, they call it dual cycles. Okay. All right. So let's look at example problems to finish off this session. So I'll give you about 5 minutes. Just have a look, and then let's give it a try. Okay. Just give it a try and understand the problem first before we go into details. Okay. Okay, a question, all right, from Matthew. All right, so the question is, can I say that smoke and soot is one of the byproducts of the Q out? Okay, not quite, Matthew. Okay, so the question by Matthew is very, very valid and it's quite interesting. Eh? So can we say that smoke and soot or particulate, the one that we just saw just now, is the byproduct of the Q out? Okay. If we look at the cycles, Q in, Q out. Okay. This Q out, Matthew, this is based on the diesel cycle, which is an idealization, not the real cycle. So the Q out over here, it replicates the exhaust. Yes, the exhaust, it replicates or it assumes the process of throwing out the particulates or the soot from the actual engine. So over here, on the cycle itself, just this cycle, we only have Q out, which is just heat. So I don't think it's right for us to say that this Q out basically contains soot plus what is called smoke or plus particulate. Okay, because this is an idealization. But in reality, yes, maybe not byproducts of the Q out, but byproducts of the exhaust. So exhaust basically contains soot, particulate, and also smoke. I think this is more accurate to say exhaust cycle or exhaust process stroke. Okay, because Q out over here is more a representation of exhaust, but not exactly the exhaust for the stroke. Okay, so I have a few more minutes to look at these questions, and then we'll try to look at the solution.
All right, so thank you for your explanation.
Okay. Okay, so I think let's have a look at these example problems. So given to us an ideal Otto cycle, a compression ratio of 8. Okay, at the beginning we have air at 100 kilopascal and 17 degrees Celsius, and 800 kilojoule over kilogram of heat is being transferred to air during constant volume heat addition process. Accounting for the variation, blah blah blah, we have to find these four problems. We have to solve these 4 problems. Okay. The first step that you need to do when you get questions is to extract the information given in terms of points and also transfer it into a diagram. So this is the first step that you should do, okay, before you start answering the question. So start by listing out what is given to us. Okay, so we know from the information given, we have R equals to V1, V2 equals to 8. We have P1 equals to 100 kilopascal. We have T1, 70 degrees Celsius, which we have to convert into Kelvin. Okay, excuse me. Okay, so this is very, very important. And then we have Q in. Okay, remember, this is not capital Q because we're given in terms of kg over kilogram, so it is a small q. So 800 kilojoule. So please, once we get all this information, we have to transfer this into the diagram. You have to do these 2 first. Most of the time, I'll give 2 marks for this. It's not just for drawing the diagram, for properly transferring the information to the diagram. So when you look over here, we have the information of P1. This is P1. Okay. And then we have information here, which is very, very important that students usually forgot. The relationship between V1, V2, and V3. Okay. So because V1 equals to V2, V1, V2 equals to 8. So to get V2 equals to V1 over 8. Okay. And since V2 is equals to V3, so you get equals to 1 over 8 V1. Okay, so transfer all the information. Then we have Q in. Q in is which is 800 kilojoule over kilogram. Okay, so write down on the diagram. Then we don't have Q out. Okay, what is the last piece of keyword or information that is given in terms of sentence, not in terms of the values? You look over here. This one, the one that I just explained just now. Accounting for the variation of specific heats. So, based on this information, if students use the approximation method, where you have to use T2, T1 equals to V1, V2, A minus 1, then this is already wrong. Is it the correct one that I'm writing up? Check. Okay, yes. So if you use this, then your method, your calculation is already wrong because you are not giving what the question asks. Okay? The question asks for variation of specific heat. Means that you need to use the specific relative volume. Sorry, balik. VR2, VR1. Okay. Okay, so let's have a look at the solution. Okay, here. This is exact analysis accounts for temperature variation. Okay, so let's have a look. Okay, so after you write down all the information, you transfer to the plot. Okay, what you need to do is list down the assumptions. So we have air standard assumptions because we're assuming we are using air. Delta KE and PE is negligible, okay, because the variation is very, very small. And more importantly is the instruction or the assumptions that has been given, which is variation of specific heat with temperature. That's what we want to do. Okay. So when we start with the diagram, that's why the diagram is very, very important. If the information that you transferred on the diagram is wrong, then your calculation will be wrong. Or if students forgot to draw the diagram, first you will lose mark. And secondly, it's very, very difficult for you to proceed with the calculation without the proper diagram. Okay, without the diagram, you will be blind. Okay, so that's why it is important for you to draw the diagram. Okay, so where should we start? So in this case, for the first question, we want to find the maximum temperature and pressure. By looking at the diagram, we know that the maximum temperature and pressure is at state 3. So our target is to find T3 and P3. But to go there, we need to start from process number 1. Okay? So at T1, this is 290 Kelvin. Remember, we are given 17 degrees Celsius. But because we're dealing with gas, if you go to table A17, okay, A17, we are dealing with Kelvin. So that's why it's important to convert degrees to Kelvin. All right. Okay, so why is it not? I hope you are looking at, okay. All right. All right, so next, we have to go to table A17. A17, look at 290 to find the information on U1 and VR1. So I'm just going to go quickly because I assume you already understand about this. Okay, so 290, okay, I already highlighted over here. This is table A17. Okay, so you have to go here, okay, find U and also the VR, okay, because we want to use, this is for the VR1 or VR2, okay, we need to use the exact value. All right, so from there, go back, you can get 206 and 676.1. Okay, so if we use the constant specific heat, okay, this is for approximate analysis, you can just use these particular equations, okay, which is much faster, but that's not answering the question. Okay, so for process 1 until 2, since we already found VR1, okay, so we have VR1, okay, and then we also know V2 divided by V1, which is 1 over R, that's given to us. So we can find VR2, okay, we substitute the equations, so we just found from the table VR1, so 8, that's given, so you get 84.51. Okay, so that's the value of VR2. So this value basically is available in the table. So to get the temperature, the corresponding temperature, remember, T accounts for the V or the VR respond or accounts for the temperature. It relates to the temperature. So to find the temperature, you have to go to the table to find the value of 84.51. So let's have a look quickly. To find the value of VR, so you look from this table, I've already highlighted. The value of 84 point something just now is located between these two values. So your answer should be between 650 and 660. So to do this, you have to interpolate, okay, which I hope everyone still remembers how to interpolate. So when you interpolate, your value is 652, and you also need to interpolate U, because we'll be using U later on. So when you interpolate, you'll get T2 and U2. So to double check whether your interpolation is right, the value is makes sense. For example, let's check back to the table, the one that I highlighted just now. It should be between 650 and 60. So because your value was 652, so your answer is right, or your interpolation is right, because it is located between the two values. Okay. So next, from there, remember this is ideal gas equation. You can use it for any processes that involve ideal gas. So from here, we want to find P2. Okay, we have all the information. We are given P1. We calculated or found T1 and T2, and we have V1 and V2. Okay, so this is ratio 8. Okay, we know all this. Substitute, you get your P2 1799. Okay, so next we proceed for process 2 to 3, which is a constant volume. So we have Q in equals to U3 minus U2. Okay, remember there is no work done, okay, because it's a straight line, so there's no area under the curve. So you have just U3 minus U2. Q in was given. Please make sure you look at the units. Very important. Sometimes students forgot. It's very different. 800 kilojoule and 800 kilojoule per kilogram. They are two different things. So please make sure you look at the units properly. So from here, you substitute our U2, we just found from the table, and we interpolate this now. Now you can get U3. So similarly, from here, you go to the table and interpolate to get temperature 3. Okay. So this is basically the values that we want, T3 and P3. So we get one of them. So how to get P3? We can use again ideal gas equation. We know P2 by now. Okay. We just calculated over here. And we know what is T3 and T2. And when you look over here, when you rearrange, you get V2 divided by V1. remember that V2 equals to V1. It's very, very important to write down over here. Sometimes you forgot because we are doing a lot of calculations. Mistakes happen. Okay, so write down so that you remember, or you can quickly understand V2 equals to V1. You substitute. Okay, basically what you get is V2 V1 is equals to 1 here. So you substitute, you get your this is for P3. So you get T3 and P3, which is question number 8, highest temperature and pressure. Okay. So proceed. The question they want to ask, they want us to find W net. Okay. So first, usually my style is write down the equation so that you understand what are the variables that you need to find. So W net is given by us equals to Q net equals to Q in minus Q out. So from this equation, this is given to us. So what we need to find is Q out, and Q out can be found by using this equation, Q1 minus Q4, or Q out equals Q4 minus Q1. Remember, sign convention. Very, very important. Okay, the heat is being released outside, so negative out, 1 minus 4. Okay, so when you substitute, so Q out equals, well, we know all this, okay, from our interpolation. So you get this, just substitute, you get your W net here. Why we need to find W net? Because C asks us to find the efficiency. Efficiency, just remember, out divided by in. So our out, this is net, 418 divided by Q in, and your efficiency is about 52%. Okay. And finally, we need to find, okay, when you look at the efficiency over here, this is by basically using not manual, but as an analysis, because you take into account the variation. Just now you need to find T1, T2, or maybe T3 by using the V, the relative volume. Okay. When you use the shortcut, remember the efficiency equation, your efficiency is about 56%. So you can see that there is about 4% differences when you use different approximation method or different method. So which one is more accurate? Okay, the answer is this one, because this takes into account the real temperature. Okay, T1, T2, T3. Over here, this is an approximation, but it gives quite a good or close value. There's a 4% differences, and actually it splits up the whole process. Okay, so these examples basically shows you there will be some differences if you use a different approximation or a different formulation. And finally, to find MEP, remember MEP is W net divided by the displacement, so V1 minus V2. So usually when you arrange, you'll get something like this. Okay, so now you need to find the only variables that you don't know, which is the volume. So volume, you can use PV MRT or PV RT. You can find here. So we know R is constant. This is available from properties table. We know what is T1. We know what is P1. Substitute. Okay. So you can get your MEP. Substitute everything, but do not forget unit conversion. Students who did not write down unit conversion, okay, I will really deduct 1 mark. Okay, so it's very, very important to get the unit conversion right. So that's basically MEP. Okay, so I think that's all for the example problems. Starting from next week or next session, I will post a video regarding the Brighton cycle for you to look and for you to watch, and hopefully we can have a discussion next Friday. Okay, all right. So I think that's all from me. Any questions before we end our session? I open the session for questions. Anyone? Nothing. All right. So I think that's it for today. Okay. Have a good weekend, everyone. Assalamualaikum and very good.
Thank you, Doctor.
Okay. Laju. Okay. Assalamualaikum.